let's look at a second example. I'm going to do it all in one video this time. So we've got some real data here. We've got moons of Saturn, and sometimes they hide the units. So if we look at the radius here of each of these moons, it's got times 10 to the 5 kilometers. That means when we're doing our final answers to these things, we need to be putting that in. Like you can see down here, 1.4 times 10 to the 5 kilometers. It's easily forgotten about. We've also got the period in days here of how long it takes them to orbit Saturn. And looking at the data, it looks like as one goes up, the other goes up. So the bigger the radius, the longer it takes to go around. If we look here, the radius, see how it's defined, is the mean radius orbit of, so it's how far they are away from Saturn. Now they've given us a form here, r equals kt to the n. If we look at how that's different, the variables here, so r and t, r is on this side of the equation, t, instead of being like the power, like it was in the first example, is now down here. We're going to move to whiteboards and we're going to investigate how that changes it.
Taking the form that they had, which is this one up here, we take logs of both sides, just like we did before. So log of the left hand side equals log of the right hand side. I put brackets in here just to make it clear that it's everything that's inside this. Next, if I've got two things multiplied together inside a log, I can use this log rule to write it as log of the first thing plus log of the second thing. And then finally, if I've got a power up here, I can bring it down. Now, we have to be careful here about what's a variable and what's a constant. Remember, the variables are the things that are in the table. So our variables here, we've got r, which is the radius, and we've got t, which is the period. So following it through, the variables, those are like the equivalent of y and x. So that bit in there is the equivalent of the y. The equivalent of the x is this bit here. It's the other variable. M is the thing that we multiply by the x, so that's, in this case, n, and then c is the constant that we add on. So we have something which is in the form y equals mx plus c. Now, if I just bring back the previous example that we had here, just overlap them a bit. The difference with the last example, if you look where the variable was, on this one it was down here, whereas on this one it was up here. The difference that makes on the last line is on the new one, the x is log of the variable, whereas on the old one, x was just a variable without log on it. So on this one, what we did is we plotted a graph where it was on the x-axis, it was just t, and on here it was log of t. The difference with this one is that when we do it, the equivalent of x now is log, and the equivalent of y is still a log. So log r. So this is what we call a log-log graph. This one, we often call it a semi-log graph. So it's still a normal variable at the bottom, but it's log of this one. So our tactic here, we need to work out what log of t was, log of r was, and then plot that, and it'll be a straight line. So it's a very subtle difference. All of the questions you will be doing are of either this type or this type. They come about half the time each. Let's carry on with this, using the computer to plug in the numbers and to plot the graph.
Okay, now I've plotted this data in exactly the same way as we had before. So here's the original data with r against t. What we're going to do is we're going to plot log t and log r. Now if you skip, say, 10 seconds back in this video, you'll notice that the equivalent of the y-axis was log r. That's the reason I put it in second. So it was r and then t, but I put it in then x, just write them in, and then y order. Just be careful that you get them the right way. In the exam, they pretty much always do it x then y anyway. Okay, well, we need to take the log of each of these things. The function here we want, if you type in log, it gives you a whole lot of options. It's log 10 we want. You can just type it in as well. So log 10 of, we're looking for t, so that one there. If I now drag that across, it's giving me log of each of these ones going along here. Right, we want to do the same thing for log r, so it equals log 10 open brackets of the r values. And again, I can just drag that across. There we go. Right, we need to draw a graph of this. Now I'm not going to bother including the names of the moons, they don't really matter. I'm just going to drag it across those ones there. So if I go to Insert and then Chart, now we're after a scatter diagram. I just scroll down a bit here, Scatter, and if you go to Customize and we want Series, and if we scroll down, there's Trend Line. Okay, now on this trend line we wanted to make it a bit bigger. So if I click on the trend line itself and then label use equation, it's drawn it in really small, but if I click on that I can go to legend font size and I'll just make it something big like that. Final thing, just like before, this scale isn't going down to 0. It doesn't really matter, but let's just click on it anyway. If I click on it and go to min value, I'm going to put 0, just so we can see clearly where the y-intercept is. On here, it's saying log r, which is our y value here, equals 0.667, that looks suspiciously close to 2/3, we'll talk more about that in a minute, times x. Now x here, if we just look at our original data, that's the log r, that's the log t, so we know that that should really be saying 0.667 log t, that's the gradient, which looks about right, plus the y-intercept here, 0.285, which again looks about right. So the numbers to write down, here's the gradient, here is the y-intercept. Let's go back to the whiteboards to finish off.
Final bit. This top line is the one that we took from the technology, where we read off the gradient and the y-intercept. This is the one from the very start of the video, where we rearranged the algebra. Notice that we've got most of the same bits. We've both got the y bit, the log r. We've both got the x bit, the log t. The gradient, well, n, we know what that equals. There's no extra work to do there. So n equals, now I could write it as 0.667. This is actually something from physics. Let's just write it as 2/3. Sometimes they come out to nice things because sometimes what we're finding here are rules actually from the world of physics. And then this last one, log, the base of that is 10, of k equals 0.285. Rearranging that for k, k is equal to 10 to the power of 0.285. Sticking that into a calculator, we've got 1.93, and that's what k is. So we've got our two values. Sticking it back into the original form, if we know what n is and we know what k is, we know that the original form is this, and so we can put it all together. R equals whatever k was, which was 1.93, multiplied by t, which is one of our variables, to the power of 2/3. Now, I'm not sure if you've done it yet in physics, but this is one of Kepler's laws of planetary motion. And we're done. After that, if you go back to the start of the video, or I'll put it under the video in my actual website, there's some follow-up questions where you're sticking values of t and sticking your values of r to work them out. That is the whole method in one video. Have a go at one from the book. These are hard, but they are the same thing every time. Over to you.